So hello, welcome to the first lecture for the 13th chapter, Nuclei, from the 8th unit, Atoms and Nuclei. So in the Atoms chapter, that's chapter 12, we had learned that most of the positive charge of the atom is concentrated in the center, or like in the middle of the atom, okay, center of the atom, and it is usually called the nucleus. So this is the structure of the atom that we had seen. Okay. Okay, so we have the central nucleus, okay, and this is positively charged, and all the electrons are actually revolving around this central nucleus. Okay, so this was the atom that we had seen. And there were experiments, usually the scattering of alpha particles. The experiments that was done by the scientists, and we saw from those experiments that actually the radius of the nucleus is actually very small compared to the radius of the atom. Okay, so that means that actually the mass of the volume of the nucleus is very, very small. Okay, so that is actually the volume of nucleus is actually 10 raised to minus of the order of 10 raised to minus 12 of the entire volume of the atom. Okay, of the atom. So you like then essentially we can say that the atom is actually very it's kind of empty. Okay, and the mass of the atom is actually concentrated in the nucleus itself. Okay, so that like more than 99.9% of the mass of the atom is actually the nucleus. So if the nucleus itself is such an important aspect or important constituent of the atom, we will try to see, okay, so what are the properties of the nucleus, or the mass, and whether it's stable, unstable, and also there are some phenomena that is associated with nucleus that you might have heard of before, that like nuclear fission, fusion, radioactivity. Okay, so these are the things that we will cover in this chapter. So first we will deal with the very important part, that is the atomic masses and the composition of nucleus. Okay, so since we have already said that the mass of an atom is very small, okay, when you compare it to other matter, for that, for the instance. So like for example, if we take, okay, so example, yeah. So for example, suppose you take carbon atom. Okay, so carbon atom is C12. Okay, so 12 is the atomic, the mass. Okay, so it's the atomic mass. Okay, this is how we denote an element. Okay, so we can see that the carbon atom, the mass of the carbon atom is actually 1.992647 into 10 raised to minus 26 kg. Okay, you can see that the order of the mass of the carbon atom is very, very small. Okay, so if we start using kg as a unit, so that is why we do not denote the mass of an atom in terms of kg. Okay, so what we use is mass unit. Okay, atomic mass unit, that is U. Okay, so 1 U is actually, you can give it as, say we are considering it for the mass of the carbon atom. Okay, so mass atom divided by 12. Why 12? Because 1U, okay, this is actually small u. 1U is equals to 1/12 of the mass of C12. Okay, so then if you calculate this, what you get is 1.99 into 2647 into 10 raised to minus 26 by 12. Okay, so that actually comes up to 1.6605 into 10 raised to minus 27 kg. So you can see that the one atomic mass unit is, it's very small when we are writing it in terms of the kg. Okay, so actually the atomic mass is usually given as integral multiples of the mass of the hydrogen atom. We know that hydrogen atom is the smallest and the lightest element. Okay, so we consider the one atomic unit to actually be the integral multiple of the mass of the hydrogen atom. Okay, mass, we are going to consider that as one atomic unit. Okay, so accurate measurements of atomic masses. How do you know that this is the atomic mass of an element? Okay, so that is usually done by using spectrometer. So and the measurement of such atomic masses actually gives you the understanding of different types of atoms of the same element. This is how uh, you can have the same element, okay, occurring as different atoms which have different atomic masses. Now such elements can be called as isotopes. Okay, so you can say that one atom or one element has a number of isotopes. And what are these isotopes? These are actually the chemical properties of these isotopes are similar, but their atomic masses actually is different. Okay, so that is what they have, same chemical properties but they have different mass. Okay, so for example, if we take example, we are going to take chlorine. Okay, so chlorine has two isotopes. Okay, so it has one isotope which has a mass of 34.98 U. Okay, why we are considering so small? This is we are considering as the integral multiple. Okay, integral multiple. Yeah. So one is 34.98 U and the other one is 36.98 U. Okay, so this is the integral multiples of the hydrogen atom, and these are the masses of the chlorine isotopes. Okay, and how much is the abundance? Okay, so abundance as in how often they occur in nature. Okay, how often do we find these isotopes? Okay, so the most abundant one is actually the 34.98. That's approximately 35. We consider 35 as the average or the atomic mass of the chlorine. So this is actually 75.4 and this is your 24.6. Okay, these are the abundances of these chlorine isotopes. Okay, so now since we have two different atoms of chlorine, like isotopes of chlorine with two different masses, we will now find the average mass then. Average mass of Cl atom. Okay, so how do you find that? We multiply the masses, okay, with the relative or with the corresponding abundance, okay, and then we add both of them. So you have 24.6 multiplied by 36.98 divided by 100. So your average mass comes out to be 35.47 U. Okay, so this is actually the mass of the chlorine atom, which we write as this. Okay, so this is for chlorine. Okay, there are other elements also which have isotopes. Okay, you have hydrogen, which you can find obviously in terms of hydrogen itself, but you also have deuterium and tritium. Okay, so you can also find isotopes of hydrogen in terms of your deuterium and tritium. Okay, so the mass of hydrogen is 10078 U, deuterium is 2.0141 U, and tritium is 3.016 0, I think, yeah, U. Okay, so hydrogen has the lightest atom, okay, and it has the, we consider it totally as one. That is why we have integral multiple of the hydrogen atom as one unit. Okay, so if we consider hydrogen, H has only, like, it has one electron, it has one proton, and it has zero. Okay, so, and it has zero neutron. We'll learn about neutrons later, but now just for understand, so we consider this. Okay, now the nucleus of the hydrogen atom only has one proton. So actually we can say that the mass of the hydrogen atom, okay, is corresponding to the mass of the proton. So from this we can find the mass of the proton. So mass of the proton is equals to 1.0784 because hydrogen has only one proton. Okay, so the entire mass of the hydrogen is actually of the proton itself. This is in U, so if we write it in kg, it is going to come up to 6726. This is 262 into 10 raised to minus 27 kg. Okay, so this is how we find the mass of the proton, which is actually equivalent to the mass of the hydrogen atom itself. Okay, and obviously you do have an electron also. Okay, so you can compare with that. And then the other two isotopes that we have said, that deuterium and tritium. Okay, so the tritium nuclei will be the heavier, the heavier atom of the hydrogen isotope, and it is usually unstable and it does not occur naturally. Okay, and usually it is produced in labs. So this is how we can find the atomic mass, and we learned about the atomic unit. Okay, now since till now we have been talking about the mass of the atom in itself, okay, but we know that the nuclei itself has, it has protons. Like right now we know that we have protons and neutrons, okay, but how do we understand that there exists another constituent of atom, which is a neutron other than the positively charged proton and the negatively charged electron? Okay, so the proton that we see in a nucleus, we can say that it carries 1 unit of fundamental charge. Okay, and it is usually, and it is stable, and all of the electrons are outside the nucleus. Okay, now after people found that you have isotopes, you have there is one particular element, okay, and it has isotopes, and all the isotopes behave chemically similar, but they have different atomic masses. Now if we only consider the presence of protons, okay, all of these have similar number of protons, but okay, so there must be another kind of another constituent or another uh, say another aspect which is actually giving this difference in masses in these isotopes. Okay, so this actually led to people understanding that there is something other than protons in the nucleus. So that is when people started saying that the nuclei of atoms, in addition to protons, have some neutral matter. Okay, and it is in the terms of multiples of basic unit. As you can see, the masses of nuclei for hydrogen can be in the ratio 1:2:3. 1 is hydrogen, 2 is deuterium, and 3 is tritium. Okay, so if this is a ratio, okay, and 1, we know that the hydrogen has 1 because it has only one proton. Okay, but deuterium and tritium also have one proton each. Then what is the kind of the factor that is actually changing the mass? Okay, and obviously we know that the electrons, okay, which are outside the atom, okay, all the electrons, that is actually the atomic number. Okay, that is the Z. Z is the atomic number. Okay, Z is the atomic number. So we know that the atomic number, and usually since the atom itself, for it to be in the neutral state, the number of protons and electrons are equal. Okay, so Z is actually the number of both protons and electrons. Okay, and the total charge of the atomic electrons would be, okay, I'll just write it here, charge, okay, of electrons can be written as minus Ze. Okay, so E is the electron, okay, and for protons in the nucleus, okay, protons, or let us write this as, sorry, nucleus, because we've still not discovered the neutrons yet. Okay, and this is the nucleus has the plus Z total charge. Okay, so the number of protons in the nucleus of the atom is actually the number of electrons. Okay, so it is equal. Okay, so number of electrons is actually number of protons, or nuclear element, nuclear constituents till now. Okay, so as we said that since the nuclei of deuterium and tritium, which are the isotopes of hydrogen, they must for them to behave similar to hydrogen, it must have only one proton. Okay, but we see that the mass differs. If the mass is differing, then there must be some neutral matter in the nuclei, okay, which can be expressed in the terms of masses. Okay, so this actually, kind of motivated a scientist called James Chadwick to, perform some experiments in which he verified the presence of neutrons. Okay, and he did that by observing the emission of neutral radiation when beryllium is an element, when beryllium nuclei were actually bombarded with alpha particles. Okay, so again, this was like, kind of the experiment that was done in the, when we studied the atoms chapter. Okay, and when he did that, he realized that this neutral radiation that is, being emitted, that is actually knocking out the protons from the light nuclei. Okay, and they had actually supposed helium and carbon and nitrogen. Okay, so the only neutral radiation that, during that time that was known was electromagnetic radiation, photons. Okay, so by applying or understanding the principles of conservation of energy and momentum, it could be, inferred that the neutral radiation actually consisted of only photons, that is the energy of the photons. Okay, so the energy of the photons will have to be much higher, okay, than the available energy of the from the bombarded alpha particles. Okay, so considering this, then they tried to find he actually put forth the existence of this neutral radiation in terms of neutral particles that became known as the neutrons. Okay, so from the conservation of energy and momentum, he was able to find out the mass of this neutron. Okay, and and he concluded that it was very much similar to the mass of the proton. Okay, so now we know the mass of the proton to, very much of high accuracy, and it is said to be 1.00866 U. You see that this is, close to the mass of the proton. Okay, we had 1.00, 7 and so on. So then that is 0.67 into 10 minus 27 kg. Okay, so this is actually the mass of the neutron that is known. Okay, and because of this discovery, Chadwick was actually, awarded the 1935 Nobel Prize in Physics, and obviously it was a very important discovery. So a free neutron, is unstable actually. Okay, a free proton is stable, but a free neutron is unstable. It decays into a proton and an electron or another, elementary constituent like antineutrino. Okay, And the mean life of a neutron, which is just outside, it is not stable, is 1,000 seconds. Okay, but it is stable inside the nucleus. Okay, so if you kind of bombard an atom, and if a neutron is released, it will decay into other elementary particle. It will not stay as neutron. Okay, but inside the nucleus of the respective atom, it is going to be stable. Okay, so now we can say that the composition of an atom and as well as actually the nucleus can be given by different kind of terms. Okay, so you have Z, that is your atomic number. Okay, this is your atomic number, and it is usually equal to the number of protons. Okay, and then you have N. Okay, N is what? It is the number of, it is also called the neutron number, or the sorry, yeah, so it is called number of neutrons, or it is called the neutron number, which is the number of neutrons. So your total atomic mass, okay, which is A, is actually the atomic mass number. Actually, it's atomic mass number. Okay, that is actually also Z plus N. Okay, so that is actually the total number of protons and neutrons. Okay, so this is the atomic mass number. Okay, so how do we denote this kind of, when we have an element? Okay, suppose for example, you take example as gold. Okay, the symbol for gold is AU. Okay, it is actually the French term for gold. Okay, AU. So the way that we write the symbol for an element is actually X. Suppose X is any of the element that you take. Okay, on top, on the left hand side, you write the atomic mass number on top and the atomic number below. Okay, so for gold, it will be AU is your symbol. Okay, AU is your symbol, and it has 197 mass, atomic mass number. Okay, and your atomic number is actually 79. So that means, okay, actually this total number of protons and neutrons can also be nucleons. Nucleons are the elementary particles that are there in the nucleus. Okay, so 197 is actually the number of 190, of the nucleons. Okay, and 79 are the number of protons. Okay, and if you minus 79 from 197, you get your number of neutrons. Okay, so this is how we can find. Okay, so the composition of isotopes of elements can then we can kind of explain. So the mass number of the isotopes will change. Okay, atomic mass number, but the atomic number remains the same. Okay, so if you consider hydrogen as the example again. Okay, hydrogen has three isotopes as in it has one as H. Okay, one as your deuterium and one is your tritium. Okay, so we can then say that actually it's written as in H only. I'm just writing this as the okay. So hydrogen will be written as 1 0. Why is it, sorry, this is not 0, this is actually going to be 1. Okay, so H will be 1 because it has only one proton, so and 0 neutrons. Okay, so 1 plus 0 will be 1. Okay, so A is equals to that. Okay, deuterium, the symbol is actually 2 plus 1. Okay, so atomic number is 2. Why? Because it has one proton and one neutron. Okay, and tritium similarly will have one proton. Okay, but it has 3 as atomic mass number. Okay, one proton or atomic number is 1, okay, for tritium, and 3 is the atomic mass number. So that is why we get it as, sorry, yeah. So it has one number of proton, but it has 2 neutrons. Okay, so this is how we can write. So these are called isotopes. Okay, so these are isotopes of hydrogen. Okay, now we saw gold. Okay, so if you take example as gold, okay, which is AU, we saw 197 as one of the, and 79. Okay, this is one of the isotope of gold. Okay, and actually gold has 32 isotopes. Okay, so all these isotopes, okay, the Z is equal, Z will be same, okay, A, okay, the A of AU is actually ranging from 173 to 204. So you can see that this is a large range, okay, and each of these isotopes will have different amount of neutrons in it, okay, but the chemical property of these elements will be the same because they have one proton. Oh, sorry, not one proton, they have the equal number of protons, so they have equal number of electrons, and most of the chemical properties are actually dealing with the number of electrons, how they interact with the different atoms. So that is why the electronic structure will be similar, and that is why they have similar chemical behavior. Okay, and that is why they are all placed in the same place in the periodic table. They are not, put in, there are not separate blocks available for these isotopes. Okay, now we have another type of, elemental category that is called the isobars. Okay, so what are isobars? That the nucleus, the nucleides actually have the same amount of same mass number A. Okay, so the example for this, we can see that if we consider a hydrogen with this, okay, and these are called isobars. Okay, when you have A is same, Z is different. Okay, these are isobars. For isotopes, you have Z is same, A is different. Okay, this is the difference between isobars and isotopes. Okay, so the nucleides will have same neutron numbers, but their atomic number Z is different. Okay, so you can have another type of elemental. Sorry, this is actually helium. Okay, so these are isobars. They this is what, this is tritium. So tritium and helium are isobars. Then you have another type of elemental category, that is isotones. What is isotones? Okay, their n is same. Okay, so number of neutrons is same. Okay, but Z is different. Okay, so examples of them are AU and HG. Okay, HG is, I think, sorry, I think it is mercury. Yeah, Hg is mercury. Okay, so gold and mercury can be called isotones. How? That they have same number of neutrons. Okay, but their atomic number is different. And since they have atomic number different, okay, so their masses are also different. Okay, but the n is same. Okay, so if you actually, kind of subtracted 197 minus 79, okay, and then you can subtract the similarly 198, okay, okay, so and suppose you have, okay, so both of them, n is actually 180, okay, so that is same for both of these. So these are called isotones. Okay, so now we understood how we can get the mass of the, the atom. which is equivalent to mass of the nucleus of the atom. We also learned that, with proton, there are other elementary constituent that is called neutrons, and they are different in number than the protons, okay, which gives us the difference in the atomic masses, okay. Now we will see what is actually the size of nucleus. Okay, so in like the previous chapter, okay, uh, where we used alpha particles, to kind of, and they were bombarded over, thin gold foils, and we had scattering of alpha particles. Okay, we had understood this, and we realized that with this experiment, they realized that there is an atomic nucleus present. Okay, and the experiment actually showed that the distance of closest approach to a gold nucleus of an alpha particle, okay, the kinetic energy of that is actually 5.5 MeV, okay, and the closest, the distance, okay, that is there is actually 4 into 10 raised to minus 4 meter, okay. Now, uh, the scattering actually begins only when it is affected by the short range nuclear forces. Okay, and we also saw that, actually Rutherford assumed the Coulomb repulsive force as the only force that was responsible for the scattering. Okay, and the positive charge that was, given to the nucleus was confined to nucleus itself. But we also, saw that the nucleus has an electron cloud around it, okay? And that is why it is, kind of very small in size compared to the entire atom. So if we keep using, high energy alpha particles, or, higher than 5.5 MeV, the distance of the closest approach to the gold will actually become smaller. Okay, and at some point the scattering will be starting to be affected by short range nuclear forces. Okay, and it will differ from Rutherford's calculations. So then what, some people did, that they started performing these scattering experiments with very fast, fast electrons instead of alpha particles. Okay, and these electrons were the projectiles that bombarded targets. Okay, and the targets were made up of different elements, and since they used different elements, they saw that the sizes of nucleus of the various of the elements that are being used can be actually measured. Okay, so what they found was that suppose a nucleus with a mass number, okay, A as the mass number, okay, and it has a radius of r, which is actually equal to r0 a raised to 1 by 3. Okay, where what is your r0? Yeah, what is your r0 is 1.2 into 10 raised to minus 15 meters. Okay, so what this means is that the volume of the nucleus, okay, it is proportional to r cube, okay, which is proportional to a. Okay, so we can say that the volume of nucleus is actually proportional to r cube, which is proportional to the atomic mass number. Okay, for all nuclei. Now, different nuclei will have, different, you can kind of understand it as, liquids with different density. The density of nuclear matter is actually approximately density of nuclear matter is actually 2.3 into 10 raised to 17 kg per meter cube. Okay, so this is the uh, density of the nuclear matter. Now this is, as you can see, is very large compared to, ordinary matter. So this is, actually ordinary matter, okay, is actually consisting of atoms, okay, and atoms in itself has a large amount of empty space. Okay, so that is why this is, kind of, the understandable when we are considering only the density of the nuclear matter. Okay, now we will see the mass energy. Okay, now there is a relation between the mass of the atom and also the energy of the atom and nucleus when we are considering in this chapter. Okay, so this was actually, understood by Einstein himself, that Einstein actually gave us the very, kind of the obviously very well known relation between energy and the mass. Okay, E is equals to mc square. Okay, so over here we can say that the energy is, equivalent to the mass m. Okay, and c is the velocity of light in vacuum. So we can say that E is actually, the and C is obviously 3 into 10 raised to 8. Okay, so experimental verification of this relation of mass energy given by Einstein is actually done by understanding the nuclear reactions among the nucleons and nuclei, and the electrons and the more recently discovered particles. So there are a lot of new particles have also been discovered which relate to the atoms. Okay, so the validation of this E is equals to mc square can be understood by, kind of considering and also studying the relations and the interactions that the elementary particles have among themselves. Okay, so they actually follow the conservation law of energy. Okay, and this states that the initial energy and the final energy are equal, provided that the energy associated with mass is also included. Okay, so this actually makes us kind of, look into the nuclear masses. Okay, and the interaction of nuclei with each other. Okay, so first to understand that, we will understand the nuclear binding energy. So till now we have seen, that the mass of the nucleus is actually equal to the total mass of the individual protons and neutrons. Okay, like if you add the mass of individual protons and neutrons, then it should be equal to the atomic mass that we have found. Okay, but actually that is not the case. What people or experimentalists have found, that the nuclear mass, the mass of the nucleus m, is actually less than the atomic mass that we have considered, and the difference in the mass of this nucleus and its constituents, okay, the del m, is actually called the mass defect. So how did people come up with the mass defect? Okay, so for example, if you consider oxygen, okay, so which has atomic mass of 16. Okay, atomic mass number is 16 and your atomic number is 8. Okay, so your mass of 8 neutrons, okay, mass of 8 neutrons is actually 8 into 1.00866 U. Okay, the mass, this is mass, okay, mass of 8 protons is actually 8 into 0.00727. Okay, and the mass of 8 electrons is actually going to be 8 into 0.00055 U. Okay, and therefore the expected mass. Okay, so the mass of one atom of O16 oxygen nucleus should be equal to 12.127. Sorry, this is 16, not 12. No. So this would be actually 16.12744 U. Okay, but from the mass spectroscopy results, okay, mass spectroscopy results, we had said that O158 was actually found to be 15.99493 U. Okay, so this difference is actually the called the mass defect. where you can have the the mass of the nucleus is actually less than the total mass. Okay, so when we try to see, okay, we can calculate this mass defect by the formula that is actually del m, that is the mass defect, is equals to z mp. Z is your atomic number, mp is your mass of proton, plus a minus z. Okay, so this is the atomic mass number minus the atomic number, mass of neutron, Mn, and minus the mass. Okay, so we can get the mass defect of all the elements that we see. Okay, but what is actually the kind of understanding of this mass defect? It is there because uh, we can see that the Einstein's equivalence of mass and energy plays a role because of this. Okay, since the mass of the oxygen nucleus is less than the sum of the masses of its constituents, okay, 8 protons and 8 neutrons in the unbound state. Okay, so the equivalent energy of the oxygen is actually oxygen nucleus is less than that of the sum of the equivalent energies of the constituents. Okay, so this is where we have the mass energy relation, the mass energy interaction, that if somebody wants to separate or break apart the oxygen nucleus into its constituents, that is 8 protons and 8 neutrons, the extra energy that is required is actually going to be del m c square. Okay, so to break an atom into number of protons and neutrons, the equivalent number, you need a energy required is going to be this. This is where you have the the mass defect comes into play. This is the extra energy that needs to be supplied. Okay, and this energy is actually equivalent to binding energy. That is, we can write it as EB. Okay, so EB is equals to del mc square. Okay, so now with the binding energy, you can there are other kind of terms that are related to this. Okay, so if you have a particular number of protons and neutrons that are brought together to form the nucleus of whatever charge that you want. Okay, so to form this nucleus of the particular charge and mass, we need an energy of EB, that is the binding energy. Okay, that will be released in the process. Okay, so this energy EB is actually the binding energy. Okay, so this is called the binding energy of the nucleus. Okay, so when you bring these together, okay, when you bring these protons and neutrons together and you want to form a nucleus, EB is released. Okay, and if we separate a nucleus into its nucleons, that is protons and neutrons, okay, we have to give this energy. Okay, so we have to give EB that time to separate these, to separate the atom into the, constituent elements, elementary particles. Okay, so usually actually we cannot do this. We cannot, break apart the nucleus in this way. So but the nuclear binding energy is still a good measure to see how well the nucleus is actually holding together. Okay, so another term which is mostly used is actually the binding energy per nucleon. Okay, so this is a better understanding of the how well bound the nucleons are in a nucleus. Okay, and it is actually given as EBN, that is binding energy per nucleon is actually the binding energy divided by the atomic mass number. Okay, atomic mass number or the number of nucleons for that matter. Okay, so this is how you can, this is also related, and this binding energy per nucleon can be understood as the average energy per nucleon that is needed to separate a nucleus into its individual nucleons. Okay, so this is the energy that needs to be supplied to break apart or to divide the atom into the protons and neutrons that is there. Okay, so with respect to that we have, plot of, this is the plot of binding energy per nucleon, okay, as a function of mass number, that is A. Okay, mass number. So you can see the plot for that. So from this plot, we can see that the binding energy per nucleon is actually, kind of constant. Okay, for atomic mass numbers that range from 30 to 170. Okay, and the binding energy per nucleon is actually lower for both lighter nuclei, that is, less than 30, as well as the heavier nuclei. Okay, so it is lower for both light and heavy nuclei. Okay, so these are the kind of, the two inferences that we can find from the plot, and the conclusions that can be, brought from this is that the force between the nucleons is actually attractive in nature, okay, and they are sufficiently strong to produce this binding energy of, it's of the of the order of few MeV per nucleon. Okay, and the constancy that we see, that the constant nature of the binding energy per nucleon between the atomic mass numbers of 30 to 170 is the result of the fact that the nuclear force is very short reached. Okay, and the property that gives the nucleons or the the it influences the given nucleons is that the only nucleons that are close to it, it has a saturation property that is related to the nuclear force. Okay, so that is the kind of the reason why we have the constant the constant nature of the binding energy. And very heavy nucleus, say, around 240, that you can see for uranium over here, which is 238. It has lower binding energy per nucleon, okay, compared to that of any that have, around 120. So 120, you can say, the molybdenum, and you have your iodine. Okay. Okay, so you can see that the binding energy is slightly lower than these two elements over here. Okay, when we're considering uranium. Okay, so that means that if a nucleus with the atomic mass of 240 breaks into two nuclei with atomic mass number 120. Okay, the nucleons will get more tightly bound. Okay, so if your uranium breaks into two different nuclei, the two different nuclei will have higher binding energy than what it had when it was when it was in the form of uranium. And the binding energy per nucleon of a fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. Okay, over here also we can see that, suppose you have two of these, any of these lighter ones, okay. So these are obviously lighter elements and they have lower binding energy, but if they fuse together and form, say, any of the nuclei that are falling in this range, they are going to have a higher binding energy than the constituent lighter nuclei. Okay, so this means that the final system will be more tightly bound than the initial system. Okay, so this are the some of the inferences that we can draw when we plot this. This is actually required for when we consider fission. Okay, and this is required when we consider nuclear fusion. Okay, so we will see the effect of this, but this is actually, what over here is actually a function of the binding energy, okay, of the nucleus. Okay, we will quickly just cover the nuclear force. Okay, so to keep the nucleus bound together, there needs to be an attractive force, okay, which needs to be strong enough. Okay, and this attractive force is actually different from the Coulomb's force, okay, that we have seen, as well as the gravitational force, okay, that exists. Okay, so this needs to be very different, and it is strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into that tiny volume, okay, that is there for the nucleus. Okay, So then the nuclear binding force that is there, it will have some features. Okay, so it is actually much stronger than Coulomb force between charges as well, or the gravitational force between the masses. So actually the nuclear force that is there is actually the strongest force that is there, okay, in nature. So the nuclear binding force will actually dominate over the Coulomb repulsive force between the protons inside the nucleus. Okay, so obviously all the positively charged protons are packed together. So you can expect some repulsion from the like charges of the protons, okay, but the nuclear force of attraction is actually stronger than this repulsive force. Okay, the nuclear force between two nucleons actually falls rapidly to zero. Okay, as their distance, is increased, more than few femtometers. So this actually leads to the, kind of saturation of forces in a medium or a large size nucleus. Okay, so that is why we have the, the constancy of the binding energy that we saw, for, heavier nucleus, they have larger nucleus also. Okay, the nuclear force that is there between the neutron neutron or proton neutron and proton proton is actually kind of the same. Okay, so that is why we can say the nuclear force is not dependent on the electric charge that is there. Okay, so this is actually the plot of the potential energy of a pair of nucleons as a function of their separation. Okay, so you can see that this is your R0. Okay, so the force, okay, the separation, for separation greater than R0, the force is attractive in nature, okay, and for separations less than R0, the force is strongly repulsive. So if you keep increasing, the force of attraction also increases. Okay, so we will stop here today, and next we will carry on with the radioactivity, and then we'll move on to fission and fusion. So thank you.